Okay, let's continue with our carbonyls. In the last class, we looked at a number of more complex carbonyls that can be understood with the concept of isolability. And we have seen that some of them can be understood as alkene or even alkyne complexes that bind side-on the transition metals. I wanted to add that this is not only a formal view, this has actually a real background. So when you look at how you can synthesize these molecules, then you find that you can indeed synthesize them from an alkyne that then binds on the transition metals in order to make the cluster compound. So for instance, this cluster here that you see can indeed be made by the dimeric cobalt carbonyl and an alkyne. So in this case, the alkyne actually replaces some of the carbonyl ligands, and then the complex rearranges in order to make the tetrahedral complex. So this, however, only as an appendix to the last class. Today I would like to talk about complexes that are related to carbonyl complexes, the number of ligands that have some similarities to the carbonyl ligands, but also some significant differences. And I would like to discuss similarities and differences. So one ligand is the hydridoligand, and hydridoligands can be also part of carbonyl compounds, because a hydride ligand can also be isolable to a carbonyl fragment, and under these conditions the two fragments combine to form what is called a carbonyl hydride. So why are, for instance, hydridoligand and tetracarbonyl cobalt ligand isolable? Well, a hydrogen has only one valence electron in a 1s orbital. So therefore, a hydrogen is a one electron fragment in a sense that requires one electron in order to fulfill the dual rule. So for that reason, it can be considered as a fragment having one valence orbital, which is that 1s orbital with one electron in it. Okay. Now the cobalt tetracarbonyl fragment also has one frontier orbital with one electron in it, and therefore these two can be considered to be isolable, and they can indeed be combined to what is called a carbonyl hydride of the composition HCOCO4. So how can you make such a carbonyl hydride? You can make it by starting out with the dicobalt octacarbonyl and hydrogen gas. So this carbonyl hydride here has an interesting property. It actually does not have, as one may expect, based on electronegativity, hydridic character, but it's actually a strong acid that has a similarity to sulfuric acid. And we can explain this due to the fact that the respective, well, anion, this COCO4 anion is a very stable anion, which leads to the fact that an H plus is relatively easily dissociated from the molecule. So there are many other carbonyl hydrides known, and one can actually tune their acidity by tuning the chemical nature of the carbonyl fragment, which involves both the metal, the carbonyl ligands, and potentially even other ligands. So, for instance, manganese tetracarbonyl fragment is a 17 valence electron fragment. Therefore, it is one frontier orbital with one electron in it. So therefore, this fragment here is also isolable to a hydrido fragment. And therefore, also these can be combined to form a stable carbonyl hydride in a similar reaction. Again, can start out from the simple dimer carbonyl reacted with hydrogen at high pressure and higher temperature. And then you get this carbonyl hydride. So now this one is also an acid, but it's a weaker acid. It only has an acidity of H2S. We may explain this weak acidity by the fact that when actually the hydrido ligand comes off, the respective anion has a manganese with the coordination number 5, which is not as ideal for orbital overlap. Okay, so in general, the properties of the hydrido carbonyls can be tuned from strongly hydridic, where the hydrogen acts more like an H- anion, to highly acidic, where the carbonyl hydride acts as a proton donor. And these properties can be tuned by, well, choosing the metal, choosing, well, the number of carbonyl ligands, but also by choosing additional ligands attached to the metal. Okay, now let's go to another ligand related to CO, which is the cyanoligand. So the cyanoligand is isoelectronic to CO, to the CO ligand. Let us see what similarities there are and what differences there are. So let us first ask again, which one is the reactive end? We have seen that for the carbonyl ligand, the carbon is the reactive end. Now for the CN minus ligands, also the carbon is the reactive end, but the difference in reactivity between the carbon and the nitrogen is smaller in comparison to the CO. So the electron pair at the nitrogen reacts more easily in comparison to the CO, and we can explain this by the fact that the electronegativity difference between C and N is smaller than the electronegativity difference between C and O, and therefore the two electron lone pairs at carbon and nitrogen are well, more similar in reactivity in comparison to the electron lone pairs at carbon and oxygen, respectively. Okay, now we can ask, well, would the CO ligand be a stronger or weaker sigma donor than the CO? Maybe if you logically think about it, you can even answer the question. So what do you think? Is a Cn minus anion a stronger or weaker sigma donor than carbon monoxide? So does it donate its electron pair at carbon more easily in a sigma fashion or less easily? What would you say? You're not sure?
I'm going to guess the cyanoligand, just on a guess.
Yeah. Why do you think so? It's actually correct.
Well, this guess isn't really related to anything inorganic chemistry associated, but I know that cyanide is typically a very deadly compound to people, so that leads me to believe that it probably has a really high binding affinity. So that would lead me to believe that, that's what led me to this conclusion.
Mm-hmm. Yeah, at least the answer has correct aspect. So the actual reason is that the Cn minus anion is negatively charged. Okay, so as it is negatively charged, the energy of the orbitals is actually increased because there's more electrostatic repulsion. Okay, so the Cn minus has a stronger tendency to get rid of electrons, to donate electrons in comparison to the CO ligand, which is neutral. So for that reason, the Cn minus ligands donates its electron paired carbon in a sigma fashion more easily than the carbon monoxide. Okay, so now what about pi accepting properties? Would you think that Cn minus ligands is a stronger or weaker pi acceptor than the carbonyl ligand?
I guess it is a weaker pi acceptor than CO.
That's correct. Can you explain why?
Yeah, for the pi acceptor, I guess it should have the empty orbitals to accept the pi electrons. However, there are the you can see the charge on the Cn, and so I don't think it is either to accept the electrons.
Correct. So the negative charge, sorry, of the Cn minus ligands decreases its tendency to accept charge, just because it's already charged, and therefore it's a weaker pi acceptor. Correct. Okay, we have seen that the CO ligand can actually stabilize metals in low oxidation states, and we can easily have carbonyls with negative oxidation states of the metal. So what do you think is the case for cyano complexes? Are they more stable with metals in high or low oxidation states?
I guess in high oxidation states will be more stable.
That's correct. Yes.
Because a higher means is lost more electrons, so it is more capable for the electrons from the cyanoligand to come in.
Yeah. So again, there are electrostatic arguments. The Cn minus anion is negatively charged, so there's electrostatic attraction between Cn minus anions and metal cations, and therefore in cyanides, you have a higher stability when the metal is in a higher oxidation state. So I'm not aware of cyano complex in which the metal actually has a negative oxidation state. Okay, very good. Then let us go to the next ligand, which is the nitroso ligand. So the nitroso ligand is not isoelectronic to the CO. We are replacing, in this case, nitrogen by carbon. And that means that we have one electron more, and that makes the NO a so-called odd molecule or a radical. So we can write its valence structure like this, with a nitrogen-oxygen double bond, 2 electron paired at the oxygen, 1 electron lone pair at the nitrogen, and a radical electron in addition at the nitrogen. So now what's the properties of this NO ligand? So now, because it's an odd molecule, it has actually two options. So again, the nitrogen atom is the reactive end. So it uses the nitrogen atom, just like the CO uses the carbon atom. But now it has, well, 3 electrons available here at the nitrogen instead of just 2. So now it can do 2 things. So it can either act as a 1 electron donor, in which it only uses this radical electron here, or it can be a 3 electron donor. Then it uses all 3 electrons. It can actually not be a 2 electron donor. That is because the radical electron is always more reactive than the other 2 electrons. So the first electron here will always be used first, and then optionally the other 2 can be used depending on the exact circumstances. Okay, so when the NO ligand is a 1 electron donor, then the nitrosyl ligand, the NO ligand, adds in a bent fashion to the metal, because the electron lone pair here at the nitrogen is sterically active. And this is how we can identify an O ligand that binds as a 1 electron donor. So here you see an example for this. So you have a complex called trans. Let's see just the nomenclature. Chloro, bis, ethylene, diamine, nitrosyl, cobalt plus. And you see here in the structure that the nitrosyl ligand binds in the 1 electron donor fashion. So the MNO bond angle in this case is typically in the range of 190 to 140 degrees. We can also identify the nitrosyl ligand as a 1 electron donor by IR. This could be the typical absorption band is located at 1520 to 1729 wave numbers. So the other possibility is that we have a 3 electron donor, and in this case, the nitrosyl ligand binds in a linear way to the nitrogen, because the electron lone pair is no longer an electron lone pair, it's involved in the bonding, so the electron lone pair is sterically no longer active. So an example here is the, well, pentacyano nitrosyl iron 2 minus A9, where you have 1, 2, 3, 4, 5 nitrosyl ligands binding to the metal here. So in this case, you see that the nitrosyl ligand is, well, pretty much linear, even though not exactly linear. The bond angle can still deviate slightly from 180 degrees. In this case, we have stretch vibration at 1610 to 1680 wave numbers. Okay, so there's another other way how we can view these complexes. We can consider also formally the NO ligand as an NO minus ligand. Okay, so in this case, when we have a bent, when we observe a bent structure, we would view the NO ligand as 2 electron donors, because 2 electrons would be donated and the other 2 electrons would remain as the electron lone pair here. Both views are acceptable. It only depends on how you actually count the electrons. So you can also view the linear structure in a different way. So instead of saying that we have a neutral NO as a 3 electron donor, we can say that we have an NO plus, which doesn't have this vertical electron here, but only these 2 electrons binding as a 2 electron donor. Okay? So now which mode the NO ligand chooses depends now on, well, what creates the maximum stability for the complex, which is often guided by the 18 electron rule. The 18 electron rule will often dictate whether a bend structure is observed or whether a linear structure is being observed. Okay. Yeah, so why can neutral NO not be a 2 electron donor? I answered this question actually already. This is because the radical electron is always more reactive than the electron lone pair, so it's always being used first, and the electron lone pair here needs to be used second. Okay, now let's go from NO ligands to phosphine ligands. So phosphine ligands are also in a way related to CO in the sense that they can have strong pi acceptor interactions, even though they are chemically significantly different to the carbonyl ligand. So at first glance, you may think that the phosphine ligand may act similarly as a ligand compared to NH3, but it's actually not the case. The phosphines interact significantly different. And we can explain this by looking into the MO diagrams of phosphine, which you see here, in comparison to ammonia, which you see here. So we discussed the MO diagram of the ammonia molecule previously, and we saw that, well, the ammonia molecule is here, this approximately non-bonding molecular orbital is the highest occupied molecular orbital. And then the LUMO is the, well, 3A1 molecular orbital. And the 2 interbonding E orbitals are then energetically located above this 3A1, which is our LUMO. So in phosphine, similarly to the ammonia molecule, we also have this 2A1 molecular orbital being the highest occupied molecular orbital. But now the order of the 2E and the 3A1 molecular orbitals are being reversed. So the 2E1s are now the LUMOs and not the 3A1, which is significantly higher. So because of the relatively low-lying 2E orbitals, energetically low-lying 2E orbitals, these 2E orbitals can now be involved in the bonding, and they can accept electrons in a pi fashion from a transition metal, and this is why phosphines can be also be good pi acceptors. NH3 does not have these abilities, again, because the 2E orbitals here are higher than the 3A1 and are not really available for bonding. Okay, so now you can actually fine-tune your phosphines by attaching the appropriate substituents in order to tune the sigma donor properties as well as the pi acceptor properties. So you see here 3 different phosphines. The trimethylphosphine, just phosphine, and the trifluorophosphine. Okay? So the methyl groups are actually electron pushing, while the fluoro groups are strongly electron withdrawing, and the hydrogen is somewhere in between. So now these properties guide or determine the energies of the HOMOs and the LUMOs respectively. So for the methyl groups, which are electron donating, we are pushing more electrons into the phosphorus, and therefore the highest occupied molecular orbital has a higher energy, okay, minus 8.8 electron volts, higher than when we have a hydrogen substituent, where then the HOMO energy is minus 10.3 electron volts, and also higher than for the PF3, where the HOMO has the lowest energy value of minus 12.5 electron volts. So accordingly, the sigma donor properties decrease as we go from the trimethylphosphine to the phosphine to the trifluorophosphine. So now what happens to the LUMOs? You see that the LUMO energies also decrease. Okay, now the LUMOs are the 2 e orbitals that can make the pi acceptor interaction. And the decrease in this case from 5.5 to 4.6 to 4.1 electron volts. So therefore, as the sigma donor properties decrease, the pi acceptor properties increase. And therefore, when you have sufficiently, electronic withdrawing groups, like in the case of the PF3, you can achieve properties that are similar to the CO ligand. So for instance, PF3 forms stable PD0 and platinum-0 complexes, while for instance CO does not. So the pi acceptor properties of PF3 are actually even greater than that of CO, and because of that you can even make complexes with palladium-0 and platinum-0, while such compounds are not known for the CO ligand, as we have learned previously. Okay. So now let's move over to what is called dihydrogen complexes. So dihydrogen means we have an H2 molecule acting as a ligand, and H2 can, like we have seen for alkenes, for instance, also bind side-on to transition metals. And in this binding mode, it simply uses its bonding sigma orbitals for sigma donation. However, in addition to that, the H2 molecule has also the sigma star orbitals, okay, which are interbonding. Okay. And you see these sigma star orbitals have suitable orbital overlap, pi orbital overlap with metal d orbitals. So therefore, the dihydrogen molecule can also make pi acceptor interactions with the metals as well. So now let's consider what happens to the bond order in the dihydrogen molecules as we increase the sigma donor interactions as well as the pi acceptor interactions. We withdraw electrons from the hydrogen-hydrogen bond that makes the hydrogen-hydrogen bond weaker, and we fill electron density in the pi star orbitals, which also makes the hydrogen-hydrogen bond weaker. so that when these interactions are just strong enough, the hydrogen-hydrogen bond will actually cleave. Okay, and then you are forming a hydride complex in which two individual hydride anions bind to the transition metal without any interaction between the two hydrogen atoms. Okay, so generally, when you have high oxidation numbers and other pi-accepting ligands, like for instance CO, then that stabilizes the dihydrogen complexes. So that means these ones of the dihydride complexes. Because when you have high oxidation numbers, you make pi acceptor interactions more difficult. Okay, and when you have all the other pi accepting ligands, then the metal has all the plenty of ability to donate electrons to the other ligands. So it has less much of a tendency to donate electrons to the hydrogen ligand, and for that reason, the decrease of the bond order in the dihydrogen molecule is not as great. Okay, so here see here actually two examples. So this here is molybdenum penta. Actually, this has to be trimethyl phosphine, penta-trimethyl phosphine dihydride, where here you have molybdenum phosphine tricarbonyl dihydrogen hydrogen complex. So in this case, you have the hydrogen-hydrogen bond cleaved, whereas in this case, the hydrogen-hydrogen bond remains intact, because in this case, you have more electron, pi-accepting ligands in comparison to this case here. Okay, then let us stop with this at this point, and let's move over to a new chapter. Let's just change the screen share again. So let us now look at dinuclear metal complexes with multiple metal bonds. So let us start with very general considerations, and let us ask, well, when two organometallic fragments interact and make metal-metal bonds, what's the maximum bond order that we could theoretically expect? So molecular theory gives you a good answer for that. So we have here plotted the metal d orbitals of the first metal, and here the metal d orbitals of the second metal. So now, which of these orbitals can we make interact? Well, first of all, we see that the dz square orbitals, this one and these here, can interact in a sigma fashion. So sigma interaction is always the strongest because they have the greatest orbital overlap. So you therefore get here this bonding sigma orbital and this interbonding sigma orbital over here. So then you see that you can interact the dxz and the dyz with another dxz and another dyz. And so the dx interacts with the dx in a pi fashion, the dyz interacts with the dyz in a pi fashion. So that gives actually these two pi orbitals and these two pi star orbitals. So pi interaction is well, less strong. Therefore, the energy difference between the pi and the pi star is less great than the energy difference between the sigma and the sigma star. So then we also have the dxy and the dx squared minus y squared. Okay, so they can interact in a sigma fashion with another dxy and another dx squared minus y squared. So the dxy would interact with the dxy to mark a bonding in an interbonding delta orbital, and the dx squared minus y squared will interact with another dx squared minus y squared to make another bonding and another interbonding molecular orbital. So now, what is the maximum bond order that we would expect? Well, you see that we have here these bonding orbitals, okay? And if we count them, then we have 1, 2, 3, 4, and 5. Okay. So from that, you would argue that the maximum bond order that we would expect is 5. So in reality, however, with a very few exceptions, only bond orders up to 4 are being observed. And the reason for this is that the dx squared minus y squared orbitals are usually unavailable to make metal-metal interactions, because they make very strong interactions with the ligands. And that is because the ligands often approach on the x and the y-axis, and that makes the dx squared and the x squared minus y squared orbitals pretty much unavailable to interact with each other. So therefore, we have bond orders between 1 and 4, or up to 4, well known, but the metal dx squared minus y squared orbitals are, as I said previously, interacting with the ligands in sigma bonding, and therefore they are not available. So only 4 metal atomic orbitals are available to form metal-metal bonds. Okay, so now what guides the bond order? We can have bond orders between 1 and 4. What guides the bond order that we will actually observe? So this will depend now on the electron configuration of the metal. Okay, so when we have a metal has a d1 electron configuration, then we have only 2 electrons available. Okay, 1 for the first metal and 1 for the second metal. So we can't make more than a single bond. Okay? But when the electron configuration is 2, then you have 2 times 2 electrons available. And then we can already create a double bond, a pi bond, in addition to the single bond, and the bond order is 2. So if we go from D2 to D3, we have 6 electrons available, and the bond order can become 3. And when we have a D4 electron configuration, then the bond order which is available is actually 4, because the number of electrons can be 8. If we go even higher with the number of electrons, then we have to start filling the interbonding orbitals, and the maximum bond order will decrease again. For D5, it will decrease to 3. For D6, it will decrease to 2. For D7, it will decrease to 1. And for D8, it will decrease to 0. Okay, so now when you look here at this example, then you see that this complex here has a chromium-chromium triple bond. So according to that, the chromium would have a D2 electron configuration. And when it has a D2 electron configuration, it would have the oxidation state +2. Okay. Sorry. So D4 electron configuration, because only when we have a D4 electron configuration, we can make a bond order of 4. So when we have a d4 electron configuration for chromium, then that must mean that the chromium must be in the oxidation state +2. Because in neutral state, the chromium has 6 electrons. If we subtract 2 electrons, then we will have 4 electrons. So we can briefly verify that the chromium here really is a d4. So when you look at the ligands, then you see that there are 1, 2, 3, 4 acetate ligands. So these acetate ligands, they have both 1 negative charge. Okay, so we have here 2 additional aqua ligands, but they don't have any charge. So you see that this overall complex here is neutral. So that means that each chromium must have a 2+ charge in order to compensate the negative charge at the acetate anions. And if the chromiums have formally a 2+ charge, then the oxidation state +2. And that means that they must have an d4 electron configuration. Okay. So now, what is experimental evidence for these metal multiple bonds? So one indication is the bond length, because there's the bond length, bond strength relationship. So typically the shorter a bond, this the higher the bond order. So you see here actually a number of tungsten complexes. And these tungsten complexes are believed to have a bond order increasing from 1 to 2 to 3 to 4. And this is supported by the fact that the bond length is actually decreasing. You see here that in this complex, we have a bond length of 272 picometers. Here it's 248 picometers, here it's 230 picometers, and here it's 221 picometers. So again, you see, for instance, when you look at this tungsten compound here, that this tungsten compound has 4 acetate ligands. Again, the acetate ligands have have 1 negative charge each. So this gives 4 negative charges. And these 4 negative charges must be compensated by 4 positive charges at the tungsten here. So we have 2 tungstens, so therefore each tungsten carries a 2+ charge formally. And if it carries a 2+ charge, then it must be in a d4 electron configuration. Okay? All right. Now, there are other indications. So, for instance, in this complex here, in this direnium complex, you find that the 2 rhenium, tetramethylrhenium units are actually in the eclipsed conformation and not in the staggered conformation. So the eclipsed conformation is actually, well, not favorable from the steric repulsion point of view. So there must be reasons that overcome steric repulsion. And what overcomes steric repulsion is that when we have the eclipsed configuration, that then the bond order between the 2 rhenium units is being increased, because dxy orbital overlap would be impossible in staggered conformation, because then these orbitals would be oriented at a 45-degree relative orientation. So the presence of a quarter-orbital bond is further supported by the short rhenium-rhenium bond distance. we can also count again the electrons and determine if rhenium is actually here in a d4 electron configuration. And you see that we have 8 methyl groups. So they have both formally a 1- charge that gives 8 negative charges. So the complex here has a 2 negative charge. So therefore, the rheniums here must have, well, 6 positive charges overall. Okay. So that means each of them must have 3 positive charges. So the rhenium must be in the oxidation state +3. So when we look in the periodic table, then the rhenium is actually in group 7. So therefore it has actually, it's a D7. So if we remove 3 electrons, then 7 minus 3, that again gives 4, which is again an argument that there's really a rhenium double bond. Quadruple bond. Okay, so this is what I wanted to say about complexes with metal-metal bonds. In the next class, we will start with organometallic reactions, and that will be the last subchapter in this course. We have 3 minutes time, but I don't think it makes much sense to start with this last chapter at this point. So I will just stop here.